Let's say you're Sir Isaac Newton and you just came up with your new theory of light. Light is made up of these little things called corpuscles and they obey the laws of Newtonian physics. Makes sense, right? You have a mirror and your things bounce right off like a ball. Now let's put some polarized sunglasses on and see what happens. So why does the water go kind of see-through? Well, this is actually due to a wave-like property of light. Okay, let's try something else. Let's shine the light through these little slits. It should make two little lines, right? Well, why are there interference patterns? Is light a wave? Well, not quite. Light actually has the properties of a wave and a particle. Crazy, right? This is called wave-particle duality, and it applies to not just light, but all particles of matter. In 1924, Louis de Broglie came up with a hypothesis that described this, and he created the formula lambda equals h on mv. What could this possibly mean? Basically, this is showing that matter, or particles with a momentum, can exhibit wave properties, where the wavelength is inversely proportional to its momentum. The formula relates momentum, which is a property only particles have, and wavelength, which is also a wave-exclusive property. He also hypothesized that electrons orbited in standing waves around the nucleus as their orbital radii are quantized according to Moore's model. A special property of standing waves is that they can only exist at specific wavelengths, or multiple of this wavelength, which supports Bohr's theory that electron energy is quantized. During 1924 to 1927, this was proved with experimental evidence from Davison and Germer's nickel crystal experiment. The experiment went like this. Electrons were fired at a nickel crystal sitting like this, with an electron detector that moved around in a circle, looking at how many electrons were scattered at different angles. At first, the scientists expected a completely random distribution of electrons emitted. However, they were surprised to see that at certain angles, there were actually peaks in the intensity of electrons. Specifically, there was a high amount of light measured at 54 volts and at 50 degrees. This was due to the electrons causing a constructive interference pattern when they were reflected off the lattice structure of atoms. This is a wave-like property where waves in phase can combine to create a wave with higher energy. Another fundamental experiment that confirmed the wave-like nature of light was the double-slit experiment. This involved shining light through a very thin slit and observing a pattern created on the wall, which ended up resembling multiple lines. This was once again due to constructive and destructive interference caused from the light actually diffracting, confirming two wave-like properties. Well, how come light is not just a wave then? This is because it still features properties that only particles can have. For example, this is shown in the photoelectric effect, where light is shined in a metal causing electrons to be thrown off. There is a minimum frequency of light required to kick off electrons, where if light was just a wave, all frequencies would kick off electrons, just given enough time to charge up, in a sense, enough energy. Overall, the theory of wave-particle duality strengthens our understanding of matter and light by explaining phenomena that Newtonian physics alone cannot. It also has major implications in the space of quantum physics, but that's a topic for another day. Okay, hello everyone. Now we're going to put this theory we just learnt into practice by doing a HSC question. So it's asking us, I'm going to just cube it quickly. Circle the verb, outline, and we're going to underline important information. Experimental evidence, and then we're concluding that light had particle properties, which is distinct, that's important, from its wave behavior. So basically this is what we just talked about, the wave-particle duality. So this here we can mention, what's it called, the photoelectric effect. I just typed the photo Okay, so we're just going to put that in. Don't worry about this. So that's our topic sentence. The photoelectric sentence. The photoelectric effect demonstrated particle qualities of light. Now we're going to do another one. This is due to classical wave theory not accounting for the discrete energy requirements to release an electron. There we go, I'll make it a bit smaller so it can fit. It's due to classical wave theory for not accounting for the discrete energy requirements to release an electron. This is due to waves being able to provide how do I word this? Continuous streams of energy, whereas a particle has momentum. And then lastly, we can say, in the case of a wave, it was theorized, any frequency work. However, the photoelectric effect disproved this theory. There we go. Look at us go. Full marks. Make that a little bit bigger. It's upside down. There we go. Okay, 2 more questions. These ones should be a bit easier because they're maths. Okay, calculate the kinetic energy gained by the electron in joules. Well, this is simple. We can use the formula work equals QV. If work is the amount of energy that the electron is getting gained, then that means energy is also equal to the kinetic energy gained. So we can equate formulas and say QV equals half mv squared. So Q is the charge of an electron, which if you get onto your formula sheet, 1.6 times 10 to the negative 19 coulombs, and simply volts is just 200. So that's 3.2 times 10 to the negative 17. So that's up. Now we're just going on to part 2. So we're just calculating the de Broglie wavelength. If we recall, the wavelength equals Planck's constant on P, which is also mv, which is going to be an easier way of writing for us. Alright, so now we have this expression for kinetic energy and a number for that. We can actually rewrite it saying half P, but it has to be balanced out with an M on the bottom. If you consider first MV is, um, let's consider it was m squared on m in this original formula. That is just p squared on 2m. So now we can use this formula in the for the calculation of momentum. So p squared on 2m, we know the mass of an electron. Um, so now we can rewrite the formula as the wavelength equals Planck's constant, 6.626 times 10 to the negative 34. And now we have, if this is, what's it called? If this is all equal to that over here, to get P by itself, we're going to have to times this 2m over here by that, and then square root both sides to get it. So really what we're going to have on the bottom here is square root 2, and then the mass of an electron, which is 9.1, and we're just going to times it by, yes, yes. So that's times it by our full answer. Okay, there we go. And we put this into the calculator, we will get an answer of 0.1 nanometers, which is also to the negative 9. No, not 19, just 9. So you know. Anyway, that's our answer. Okay, now we can see if we're right. So we referenced this photoelectric effect. We did that, mentioned the wave theory, and we said it was incompatible. We found the answer. We don't even make an attempt. Of course we got it right. And we found the answer for this one. So overall, full marks. Yippee.